Hi everyone, I'm Daniel, a final year PhD student from the PDL at Carnegie Mellon. And here with me in the room today is my advisor Greg and Hao from Matter's Cache Leap team. And so for the past half decade, we've been collaborating with our friends at Matter, and today I'm going to present another fruit of that collaboration, Baleen. And so Baleen is a type of whale that filter feeds, and it's also the name of our cache that uses ML to decide what should be put into or emitted into flash caches for bulk storage systems. To be sure we're all on the same page, I'm talking about this exabyte scale bulk storage systems that fulfill most storage needs in hyperscaler data centers. And to store these exabytes efficiently, you need lots of hard disks, and then you need to over-provision even more disks so that you can handle the IOPS and bandwidth of real-time demand. And the key part of these systems are caches, and not just DRAM caches, but huge flash caches that soak up all this backend load. And reducing load means less hard disks that you need to over-provision. And so when you can improve these flash caching policies, you can save even more hard disks and reduce costs further. But the big problem with flash is that it has limited write endurance, and it means that you need to limit your long-term flash write rate so that you don't burn out and have to replace your flash drives prematurely. And so a good policy has to reduce writes and reduce the number of SSDs that you need in the long run. So there are two key contributors to cost: the hard disks that you need to serve peak load and the SSDs that you need in the long run for flash caching. And our system, Baleen, is able to reduce estimated costs by 17% by reducing the backend load, and thus the number of disks you need to serve that load, while balancing that against the cost of flash drive replacement. Optimizing these two constraints is challenging, and it's only going to get more important with denser storage, with the trend towards less IOs per terabyte in this, and the trend towards lower flash endurance. And so, how do we achieve this? We exploit a new cache residency model that we call episodes that we use to train ML emission and ML prefetching, and we optimize those policies for end-to-end metric that we call disk save time. As far as we know, we're the first cache to optimize for disk save time at the peak. And the biggest thing that you should take away from this talk is how we can use the concept of episodes to train ML for flash caching. Why use ML? So with flash, you're trying to capture the next level of hits that DRAM didn't, which is a hard problem with plenty of room to improve. And second, heuristics regress on some workloads, and with ML, you can train different models for each workload and thus mitigate that, and thus it is worth it to spend the extra effort to do ML. Now I'm going to dive into how caching works in bulk storage, and these systems are block storage systems, meaning that clients access a fixed range within fixed size, a byte range, within fixed size 8 megabyte blocks, and these blocks don't overlap. And these blocks live on hard disks, which live on hosts, and each cluster can span an entire data center and have thousands of these hosts. So I'm going to look at what happens for one block on one host without loss of generality. And so without a cache, you need I/O on the back end for every request on the right. And the flash cache operates at a smaller granularity, meaning that it makes decisions about what should go into the cache in terms of this 128 kilobyte segments. If everything that you need to fulfill your client request is in cache, you see all the green hits, that you get to save the I/O. But if there's even just one miss shown in red, this causes this I/O on the back end. And so we want to reduce this I/O without causing excessive flash writes. But we don't want to emit everything into cache, so we need an emission policy to filter those red cache misses. And also, it might make sense to prefetch more segments now and amortize. If you're already going to disk to fetch something, fetch more now and store into cache. And of course, like every other cache, there's a problem of when do you want to evict the item. And so all these policies, they try to decide what you should put in your cache now and for how long to reduce the backend load in the system. And in Baleen, we focus on the first two, since flash writes, you incur those costs at the time of emission or prefetching. And so we put more effort into having an advanced emission and prefetching policy, and then we have a simple eviction policy like LRU. So our metric is disk save time, and why not miss rates? And the answer is that varying I/O size. If I/Os don't vary in size, then I/O hit rate or byte miss rate is sufficient. But if they do vary in size, which is the case for a lot of workloads, then neither will tell the full story, and you need to optimize this state time to properly balance these two constraints. And otherwise, you can go down the wrong path in optimizing your cache. And so this state time this state can only do one thing at one time, and that's why this state time is a limited resource. And so a hard disk performing I/O, it needs a constant positioning time before it can read data off the disk. And so when I/Os are all small, you're limited by IOPS or I/Os per second. And when I/Os are all large, then the disk state time spends more time reading data and you're limited by bandwidth. And so disk state time is a weighted sum of the number of I/Os that you need and the number of bytes that you need to fetch. Now I'm going to talk about our episodes model that we are proposing. And first, I'm going to talk about why not do the obvious thing and train on assessors. And so a lot of forms of ML that we think about are supervised learning, meaning you have a set of training examples, you know what is right and what is the right label for this example, and so the ML model tries to extrapolate, tries to predict, use the knowledge gained from the current data set. And so what does it look like for ML for caching? You have a trace of assessors, and then you want labels for each assessor. Do I admit it into the cache or not? But it's hard to reason about what you want to do because what you decide is going to affect the contents of your cache and your future decisions. And this also tends to by just treating each assess equally, it overfits on things that are actually easy to decide, and it underfits on the examples at the margin that actually distinguish good policies from the best policies. And so the message here is that training on assessors is non-trivial. And so we propose to train on episodes instead, and episodes are groups of assessors, temporal groups that correspond to the item's time in cache from admission to eviction if you were to admit it on the first access. And I'm going to illustrate that with an example soon, but first I'm going to give you some intuition for why episodes make sense. And so they map better to the decisions that a policy needs to make. It's the right granularity. Instead of focusing on looking at all accesses, we focus on the first access. We avoid overfitting on those super popular blocks that I mentioned that may only have one miss and thus only be actually one episode. And episodes also help us come up with the accurate labels and the accurate cost and benefit functions that define on the time from admission to eviction instead of using a sliding window or just looking ahead in the future and arbitrary time. I'm going to illustrate episodes now, and the x-axis is time and the y-axis is byte index, and I'm showing here 7 accessors to this block. And so if the cache admits this block right at the start, it's going to get a miss at the first time the cache sees it, and then 2 hits, and then because there's a really long gap in time there, when it's unused, it gets evicted. And so likewise, for that 4th access there, if it gets admitted there, it's going to get 3 hits and then get evicted. And so we want to group these 7 accessors into 2 episodes that correspond to the item's possible residency in cache from admission to eviction. And instead of having 7 decision points, you just have 2 now, and you can decide on them independently. So I'm going to explain how we efficiently generate these episodes from a trace that only contains accessors. And so one way you can do it, of course, is to run an online simulation, but there's an easier and efficient way to do it offline. And the key is knowing when eviction happens. And the time that the item stays in cache after the last access is what cache people call the eviction age. How much logical time will pass before an item gets evicted if it's not reused. And so we can model an LRU cache with a constant eviction age. And if we think about the intervariable times of these blocks, meaning the time between one access and the next, and so I'm going to color these arrows based on whether they're larger than the eviction age of the cache, which is a property of the cache that we can measure from simulations. And they're all green except for those 2 red arrows because they're larger than the assumed eviction age. And so we can split these accessors into episodes whenever the intervariable time is larger than the assumed eviction age. Say, if And so if you have a bunch of accesses today and you have a bunch of accesses tomorrow for the same block, and the cache, and assume age of the cache is say 2 hours, then those accesses that today will be treated as one episode, and those accesses tomorrow will be treated as another episode. Now I'm going to focus on just episode 1 and reason about it. And so to give some intuition about how these episodes are useful. And so once you have grouped them, you can forget about the exact access times. You can just focus on the access order. And so this helps to remove the dependencies. And so one reason we created episodes is to make ML more effective and focus on the what actually matters and get rid of the extra the information. And so we want to train our episodes and focus on the beginning of episodes because that is when the admission policy is probably going to see the block, and then it helps us distinguish between episodes that are sort of the middle value ones and the margin, the episodes that dictate the differences between admission algorithms. And so when you're considering whether or not to admit something, and more importantly, whether the ML algorithm should consider whether or not to admit something, is that you want to define you want to look at the first access, and the value you get out of it is the set of hits, and that's this hit time that you save for based on those hits, and the cost is the number of flash writes you need to admit that episode. And so we use both of these things to do a better job of training the algorithm to admit things that have high value and admit them early in the episode. So we went on to design episode-based policies to answer what does good look like. And episodes enables offline analysis of what a perfect, or at least approximation of perfect, admission policy might do. And I won't have time for the details, but it allows us to efficiently explore the design space of potential improvements or configuration changes. And so what you need to know right now is that our OPT scores every episode, and for instance, on the episode just now, this might be what it looks like, and then it emits the highest scoring episodes based on a flash write rate budget cutoff. And so it produces binary labels that an ML model like Baleen can then use. To train prefetching, we also use episode knowledge, and we train regression models on what we call OPT range. And we found that OPT range which is, even though it's pretty simple, it's just the smallest range that covers all segments seen during the episode. It actually works pretty well, and prefetching actually accounts for most of the reduction in peak disk time. But we found in order to capture that benefit, you actually need two things. You need a good admission policy, because prefetching on the top of a baseline admission policy will actually hurt instead of help you. And it's not enough to predict the range, because the range could be quite different from optimal. The ML model will make mistakes. And so we needed an extra ML model to estimate how confident we are in our prediction to decide whether to proceed with prefetching or not. So all these policies, they help us reduce this time for a fixed flash write rate budget. And then the question is, what flash write rate budget should we use? And how do we balance the cost of those extra flash writes that I'm going to use in order to save hard disk load? So the two big parts of cost, hard disk cost and SSD cost, and we have a TCO function based on Google's cache tag paper. And so if we have the relative cost on flash and hard disk, we can then run a simulation and get peak disk time for different flash write rates, and then we can balance the cost of the cost reduction from reducing peak load, and thus the number of hard disks we need to serve that load, versus the amount of flash writes that we're using that will affect how much flash drives we need to buy in the long run. And so Baleen TCO is a variant that we developed that picks the optimal flash write rate for each workload. So in our evaluation, we evaluated on 7 production workloads from Matter, and we And so each of those workloads comes from one of those huge classes that I mentioned, which actually, and so there are lots of tenants like data warehouse and blob storage, and each of those tenants in turn serves hundreds of applications. And there's more detail on that in the tectonic paper, and we have also released the traces and the simulator code that we have used in this paper. In our evaluation, we compare to 3 baseline policies. Random admission is simple, but it's still used out there because it requires no state. The strongest non-ML baseline, reject X, meaning that for X equals to 1, this item is always going to reject item the first time it sees it. And cache-lib ML, a production ML policy that's trained on assessors. So our training process is done offline on the first day of a trace, and we take the highest disk time from the next 6 days, and we compare that between policies. So, for instance, these are the simulated this load over time for 2 policies, and so lower is going to be better. And so I'm going to recap. And so how do we get from there to cost? I'm going to recap the connection, and that is that by lowering the peak load, we can have less hard disks and backend servers that we need to serve that peak load, and then thus we can lower the total cost of the system. So now I'm going to show you the key graph of our paper, and so on the y-axis is estimated cost, and we normalize this based like to our baseline, and this is going to be, and so this is going to be an average across all 7 traces, and I'm going to show you different policies. And so on the left here, I have the 3 baselines: CoinFlip, reject X, cache-lib ML, and then on the right is Baleen TCL, which is our best, which saves 17% in TCL. And this varies across traces, but it's always the best policy on each workload. It doesn't suffer any regressions on any of the 7 traces. And in case you are interested, we have in what it looks like in terms of a metric you're more familiar with. It saves 14% less I/O misses, and there's more detail in the paper on that. So how do we break down this benefit? And so prefetching accounts for most of this benefit. And so what I brought up here are 2 extra bars here, but Baleen no prefetch and Baleen. So the biggest difference between any 2 bars is accounted for by prefetching. And then if willing to use to set a different flash write rate for each workload instead of using a static one, you can get the extra benefit between the last 2 bars over there. So since prefetching matters the most, I'm going to talk about what we need for prefetching to work. So firstly, we found that adding prefetching policies to static emission policies like reject X actually hurts instead of helps. So even though in the previous graph, the ML may not have seemed to help by much by itself, it's actually essential to the performance of prefetching and our whole system. And so the takeaway is that when you apply ML to one part of the system, it's important to look at the other parts of the system that you're applying ML to, and it all needs to work together. And also, we found that, also as a reminder, we needed not just the ML range model to know what to prefetch, but we also needed an extra model ML to be selective about when to prefetch and not, and so evaluate how confident we are in our prediction. That brings me to my conclusion. And so Baleen reduces cost by 17%, and how we do that is with our episodes model that guide ML training, and these policies optimize for disk state time, and so we have that OPT guided admission, and then we have prefetching that predicts what to prefetch and also when to prefetch. My current work is on what happens in the future. How do we deal with changes in the workload distribution. And so if you're interested in that, feel free to follow up with me later. And so that brings me to the end of my talk, and thank you for listening, and I'll be happy to take any questions.